Hello and welcome to the Swift Tuition YouTube channel. In this video I'll be attempting something a little on the ambitious side, which is to try and cover the entirety of sequences and series in just an hour. Now, for the sake of making this as comprehensive a guide as possible, I want to start from the beginning, the definitions. What is a sequence and what is a series? Now here I have taken 5 shapes and I have ordered them in a particular way, and I have separated each shape with a semicolon. Now, in the first position we have a triangle. In the second position we have a square/rectangle. Next one we have a pentagon. Next one we have a hexagon, and then in the final one we have a heptagon. 3, 4, 5, 6, and 7 sides. Now, hearing me say that out loud, you may have noticed something, that I have ordered them in a particular way. The first shape has 3 sides, the next one has 4 sides, the next one has 5 sides, and then so on, right? And that's essentially what a sequence is. It's when you take, in the mathematical context, you take numbers and then you order them in a particular way such that there is a pattern in the way that they are ordered. So in the n is equal to 1, this is a position. In the first position of the sequence, we have a triangle. In the second position of the sequence, we have a square. Now obviously we can't do much with shapes in the context of sequences and series. So what I will do then is associate a number to each shape. What number would you associate to a triangle? Well, obviously 3, 4, 5, 6, and 7. And then now we have created what is a term number. Now I like to compare term number with y and n with x. Why do I do that? Because that's essentially what we're doing. We know we will essentially be creating an equation that looks something like Tn is equal to Bn plus c, which is very similar to mx plus c. Y is equal to mx plus c, and that's essentially what we have done. The only two major differences that I would say with sequences and series and functions is that, first of all, when you're doing functions, you can see that it's continuous over here, right? Everything is connected and continues from negative infinity to positive infinity. Now, when you're dealing with series, the sequences and series section, you'll notice that we can only have discrete n values, meaning n can only be equal to 1, 2, 3, 4, 5. N can only be equal to those very discrete values. You can't have n equal to, like in this particular case, y would have been x would have been equal to 0.5. You can't. That does not exist. Okay. N can only be a discrete number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Can only be like that. And second thing is n can only be a whole number excluding 0. So that means that we're not going to have negative n values. We can only have positive n values. And that is basically the major differences. But I would like for you to kind of bear in mind the same principles that you would bear in mind when you're dealing with functions when you're working with sequences and series, as it may help you quite a lot. So just to recap, at my first position, I have an answer of 3, a term number of 3. At my third position, 5, and you can see the rest. Now we can create an equation that kind of models what is happening mathematically. So Tn is equal to Bn plus c. We could solve it like this, but there's obviously an easier way to do that, and we have that in our formula sheet. That would be the following equation: a plus n minus 1 multiplied by d. D being the common difference. So this particular equation over here. So we know then that we can reuse that instead if we're struggling to use this one. When giving your final answer, I would advise you to put it in this form because that's simplified form. But when you're trying to find that Tn, the term number, then, or in other words, you may sometimes phrase it as the nth term. When you're trying to find the nth term, it may be easier to use the formula in your formula sheets. Right, and then what does a represent? A represents the first term in the sequence. In this particular case, a is 3. So we're going to put a 3 over there. 3 plus n minus 1. N just represents the nth term. It's basically your x. You remember when we're doing y is equal to mx plus c, we try to find an m, we try to find a c, and then we leave x and y as variables because when we change our input value, our n value, our output value, in other words, our Tn value is going to change in this particular context. So we're going to leave n like that. When you're trying to find if they say find the nth term, then you're going to leave n. There's nothing that you substitute for n. N minus 1 multiplied by d. D is basically the common difference. The difference that you get when you get when you take the number to the right and you subtract it from the number to the left, directly to the left of it. So we're going to put a common difference of 1. So that's 1 over there. And it's just a matter of simplifying this particular expression. So 1 multiplied by -1 would have been -1. -1 plus 3 is going to be +2. So +2. And then 1 multiplied by n is just n. So I have a term number, or an nth term of n plus 2. So that is how you would answer an equation that asks you to find the term number for this particular expression. Now that we have the term number, there's a lot more that we can kind of work with now. Okay, so we have the equation that kind of determines this, that kind of defines this particular sequence, the sequence that we're given, that I gave you, the triangle, square, etc. Right? And let's just check if it works. If you interested in the third position, you can see that I put a 3 over there and I get an output value of 5. All right, I put a 3 here and I get an output value of 5, and that's exactly what I'm looking for. And I know that everything's correct. If it works with 2 or 3, then you probably have the right expression. So make sure that you don't just check with 1. You have to check with at least 2 to see that it works consistently throughout. Okay, so now that's my Tn. That is my nth term. Now sometimes I may be interested in the sum. Okay, sometimes I may want to know what is the sum that you get when you take this term and add it to this term and add it to this term. In other words, I take 4, I add it to 5, and I add that to 6. You can see that I didn't start at the 3. I didn't start at here and I didn't end at the very end of here. I started at the second position and I ended at the fourth position. I didn't start at the first to end to the fifth. So I only was interested in parts of the sequence. Now this is where the sigma notation becomes helpful to kind of represent this. The sigma notation looks something like this, and then you have this, you have this here, and then you have this over here. Now what you put over here is the equation that defines the sequence. In this particular context, the equation that defines the sequence is n plus 2. So I'm going to put an n plus 2 over here. What I put at the top over here is the final term. Where do I end in the sequence? Well, you can see I'm not starting at the, okay, no, I'm actually working with the bottom first. What you put at the bottom is where you start in the sequence. Remember, we didn't start at the first position. We started at the second position. So that's what you're going to do. You're going to say n is equal to 2. And then where did we end? Well, we ended, let me just add a 2 over here. And then we end in the 2, 3, 4. We end at the fourth position. So I'll just put a 4 at the top over here. So now I have enough information to represent what I just want to do over here. What this thing says now is the sum of this particular term, n plus 2, starting from the second position and ending on the fourth position of the sequence, is equal to, and that's what we'd be trying to find. Now the question that we're dealing with asks us to find obviously the sum starting from the second position ending on the fourth position of this particular sequence, n plus 2. How do we do that? Well, we have a formula sheet for that. Let's pull out a formula sheet. As you can see in my formula sheet, I have this thing over here. When you see the s subscript n, that just means sum to the nth term. Right, so what do I do? Sum to the nth term is equal to, and then there's my expression over here. Now let's talk about each individual element of this particular equation. This n over here is the number of terms in that you're dealing with. Now, how do you know the number of terms? Obviously over here it's quite simple to see. We can see that it's just 1, 2, 3. You just count 1, you just count 2, and then there's your third position over there. So that's pretty straightforward. But if you had a whole lot more, that would become a little tedious if you have to count every individual thing for that. So look at the number 4 and then look at the number 2. And then what do you think, what can I do with these numbers to get an answer of 3? Well, you'll notice that if I take the number 4 and I subtract it from the number 2 and then I add 1 to that, then I'll get 3. And then that's a constant rule that you can do. When you're trying to find n when you're given things in sigma notation, that's all you have to do. You take the top, you subtract the bottom from it, and then you add 1 to their difference, right? Obviously there's no point in doing this because BODMAS is left to right, but I just want you to focus on this. So top minus bottom, you find that, and then you add 1 to that particular thing. So now we know what we can do. First of all, let's predict the answer. Obviously 4 plus 5, that's 9, 9 plus 6, that's 15. But now I just want to be able to show this mathematically, how that works. 4, okay, so I know I'm going to take the top, which is going to be, top 4 minus 2 minus bottom 2 plus 1 3. So I'm going to take 3 over 2. I'm just now substituting things into this equation, and then I'm going to do 2 multiplied by a, and then a is the first term. Now here is where you have to be really careful, because the first term of the original sequence is of course 3, but we're not starting there. That's not the first term that we're interested in when we're calculating our series. The first term that we're interested in is our starting point of the series, the one at the second position. So what you're going to substitute over here is not 3, but rather 4. You're going to substitute 4 there, and then you're going to add n minus 1. Again, we've already calculated our n, so that's 3 minus 1, and then you multiply the difference from that. Remember, we're expecting an answer of 15. Multiply by the difference. Obviously I added 1 to each thing, plus 1, so we can close our brackets, and then we expect an answer of 15. Do we get an answer of 15? We do. So we did everything correctly, so we're glad. Now though, there's another equation that you won't find in the formula sheet, but I really want you to bear that in mind, because it may really save you a lot of time, and sometimes it'll be really difficult to try to use this equation in order to find the answer. So all you do is you keep everything outside of the brackets the same, and then you just replace what's inside the brackets. So inside here, all I'm going to replace it with is a plus tn, or l. Okay, so what this basically means is you replace it with the first term and the final term of the sequence. So that is in the case where you know the first term and the final term of the sequence. In this particular case, we do know the first term and the final term of the sequence. We already determined that the first term is equal to 4, that we're interested in, is equal to 4. And then we are going to add the final term of the sequence, which is, which is 6, which would be 6. And then we get an answer of 15 as well. So both of them will yield the exact same answer. So please bear this equation in mind. You may not always see it, but it is there. Okay, it is there. So please do not. Okay, let me rephrase that. You won't find this in your formula sheets. It will not be in your formula sheets, but please know to use it. Know that it exists and that you can use it to solve your problems. I'll have a neater version of this infographic on our Instagram page, and if you want to download it on our, just message us on the WhatsApp number. But essentially this is basically what we'll cover in this video. So we'll be doing some problems dealing with sequences, arithmetic, quadratic, and geometric, and you can see these are the defining traits underneath over here. And then we'll be doing the same thing with arithmetic and geometric, as well as a special case of geometric series, which is known as the sum to infinity. And sum to infinity is equal to a over 1 over r, when r is greater than -1 but less than 1, and r cannot be equal to 0. Obviously you can't have a common ratio of 0. Anyway, so yeah, that's basically broadly what we will be covering, and we'll jump right into the questions. Now, before we do begin, I just want to draw your attention to this PDF and the similar ones that we'll be creating for all subjects. Well, not all subjects. We're starting with maths, then we'll be adding physics, then we'll be adding English, we'll be adding Afrikaans this year. Next year we'll be adding other subjects, but those are all the subjects that'll be coming this year. Probably maths, we'll see. But essentially this is what you do. You look over here and then you can see the table of contents, and let's say you want to work on the sequences and series paper for 2018 IEB. Then you just jump over here and then you click on that, and it'll take you straight to the sequences and series paper for the for the IEB paper, 2018 IEB. And you can do that for every other paper. Every other paper from 2016 to 2022. 2022 papers haven't really been released yet, so we will add them as they're released. So just message us on our WhatsApp number, and we shall add you to the WhatsApp groups, and in the group description you'll find the drive, and in that drive you'll find everything. So any announcements that we'll make, we'll be announcing them on those groups, so do join. We're going to be releasing a full course that's going to take you from knowing absolutely nothing to knowing everything that you need to be able to ace your exams later on in the year. So if you want to be able to participate in that, be part of the WhatsApp group, so that as soon as we launch it, let's say we have also discounts for that, those will be primarily announced to people in the WhatsApp groups. So yeah, that's just a friendly announcement. Now we're going to start with with arithmetic sequences and series, and we're just going to start from the very beginning, the 2016 paper. Right. In question 2 of the DBE 2016 paper, we're given the following arithmetic sequence. Now, in this particular case, we're not asked to determine what type of a sequence this is. In some cases, we will be asked to determine. But in this particular case, we're just given a sequence, and then we're told that it's arithmetic. So half of the part of the job has already been done for us. Now, knowing that it's an arithmetic sequence, we know the tools at our disposal. We know that we could be using this equation, or possibly if it turns into to be a series, we'll end up using this equation over here or this equation over here, and just know what equation goes with what, and just what tools are at your disposal for whatever section that you're dealing with. Now let's read the problem. Given the finite sequence 5, 1, -3, blank, blah 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 blah, -83, -87, write down the fourth term of the sequence. Now this is pretty straightforward because it's the term directly after the -3, so we don't have to do any maths for that. It is a one mark question as well. To get from 5 to 1, we minused 4 to get there, and because you know it's arithmetic, the first difference is going to be common, so we now have to minus 4 again to get to -3, and then minus 4 to get to the next answer. So the answer for 2.1 is simply -7, because that would be the fourth term if it was given to us. So -7 would simply be the answer. Now 2.2 asks us to calculate the number of terms in the sequence. So we know this is 5, we know this is 1, we know this is -3, and then a bunch of stuff happened in the middle here, and then we have -83 and -87. Now what you'll notice is that this is at n is equal to 1. This is at the first position of the sequence. This is at n is equal to 2, the second position of the sequence. This is at n is equal to 3, the third position of the sequence. And obviously, if you minus 4, we'd have to minus 4 a couple of times in order to get to -87. I love it when the question is simple enough to have a prediction of what I think the answer should be. So what do I think the answer should be? Well, I know I know -7 is at the fourth position, so I can just minus 4 from that. That will get me to the fifth position, sixth position, seventh position, 8th, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So I know that this is at the 23rd position, and I know that this is at the 24th position. So the answer should be 24. Now, how do I actually show that mathematically? Let's look at our formula sheets. So you can see in our formula sheets, in fact, let me actually use this chart instead. You can see that the equation I can use is this one over here. This one is not that practical because it doesn't give us much information that we can actually work with. So when you're giving your nth term, give it in that form, bn plus c. But when you're trying to determine the nth term, use the second version, a plus n minus 1 multiplied by d. So I write down my equation because I know that's what I'm going to have to use. But in order to be able to solve an equation, you need to know every variable except for 1. So do I know Tn? Yes, I do. I know the nth term over here, the number that you get is going to be -87. So that's -87 over there. Then do I know n? No, I don't. That's what I'm trying to determine. I've predicted it's going to be 24, but I haven't shown that mathematically. Do I know a? Yes, I do know the first term. The first term is obviously going to be 5. So I'm going to put 5 down. And do I know the difference, the common difference? I do. I minus 4. Okay, so I've got everything that I need. I just need n. So I can actually manipulate the equation over here. If you can't do that, that's okay. But I can tell that n is going to be equal to Tn minus a divided by d plus 1. Okay, you don't have to do this, but you can just substitute and then solve afterwards. Okay, and I can substitute that -87 minus 5 over 5 plus 1. I made a slight mistake. This is obviously the common difference, so this should be -4. Okay, so I get an answer of 24. So I was able to tell because I already had a prediction, and when I used the answer of 5, I got this number over here. Now, there are two reasons why I was able to tell that that was wrong. The first reason is because I already had a prediction of 24 and it wasn't aligning to my prediction. So either one thing or the other was wrong. But the reason why I knew that my prediction was correct is because you can't get a negative 87.5 position. You can only get discrete numbers 1, 2, 3, and they can only be whole numbers, right? So I knew that then that answer is incorrect, and I just rechecked. Oh, I divided by the wrong number. I was supposed to divide by -4. So after doing this thing, you get n is equal to 24, and that would obviously be then your answer. Now 2.3 asks us to calculate the sum of all the negative numbers in the sequence. Now what I want you to try and do for yourself first is to pause this video and to try and write this in this expression. What do you write here, what do you put here, and what do you put here? Try and do that first and then I will explain. Okay, so let me just move this around. Okay, let me actually just minimize this. Okay, so what we put over here is where we're starting off, our starting position in the original sequence. Calculate the sum of all the negative numbers in the sequence. Remember, 5 and 1 are not negative numbers, so we're starting in the third position of the sequence. So we're going to put n is equal to 3 over here. And then where do we end off in the sequence? Well, we are then going to end off at the negative 80 negative 87, which is the 24th position. 24. Okay, and this is with the original sequence. So I can put the original sequence down as what was it? Okay, I guess this is the downside to doing what I did. This is going to be 5 plus n minus 1 multiplied by -4. That'll be -4n, -4 plus 5. That'll be plus 1. So -4n plus 1. That's what goes over here. Because I take the original sequence, the -4n plus 1 sequence, and then I start from the third position of that sequence. Okay, and then we continue from there, 3 in, and then you go up until the 24th position of the sequence. Alright, now how do we do the maths of this? Well, we have all the information we need. We can actually just I'd rather use my a plus l equation. So I take this, I take n over 2, that's top minus bottom, 24 minus 3 is 21, 21 plus 2, that's 22, 22, what? 24 minus 3, that's 21, 21 plus 1, that's 22, yes, divided by 2, and then a plus l, the first term of the sequence. Remember, we're talking about our starting position, not the first term of the original sequence, but the first term that we're starting from. We're not going to start from, I think it was 5, if I'm not mistaken. We're not going to start from 5. We are going to start from -3. So that's what you're going to put over here as your first term. -3 plus, and where do we end off? We end off at 24. Sorry, no, not 24. We end off at -87. -87, so I can just put -87 like that, and then you get an answer of -990, and you can just try to the other one and you'll realize that you get the exact same answer, -990. As an exercise for you, what I want you to do is to do, just for your own sake, n is equal to 1, and what would this be then if n is equal to 1? This would be 22, right? That is correct. Okay, so what I want you to do is to find a new negative fn plus 1 for if you were to start at -3. So if this thing that didn't even exist, what would our new expression be? If this was the original sequence, obviously then we'd be starting from the first position and ending at the 22nd position, right? Because these first two terms don't exist. So what would the new thing be over here? And then try to calculate the expression for that. Alternatively, you could have done the sum for every single thing and then subtracted 5 plus 1 from that, because we know that's excluded. We don't want the sum of the positive numbers. And then you can just see how the memo does that, as well as alternative ways of getting to the same answer. Now to move on to the following quadratic number pattern. Here we have -1x, -1 is the first term, x is the next term, 3 is the next term, and then x plus 8 is the final term. And we are asked to calculate the value or values of x. Now, how would we go about answering this particular problem? Well, x minus minus 1, we're trying to find the first difference first, because remember the second difference is what's the same. So we have to first find the first difference. So let's create a sequence from the first difference. X minus minus 1, that's going to be x plus 1. 3 minus x, remember it's right minus left. 3 minus x, and then right minus left, that's x. And then 8 minus 3, that's going to be positive 5. And then we're going to do the same thing in the next line. Negative x minus x, that's negative 2x. 3 plus 1, that's going to be positive 2. Sorry, 3 minus 1 is going to be positive 2. 5 minus 3, that's 2. And then x minus negative x is going to be x minus x, that's going to be plus 2x. Okay, then we can equate these to each other because the second difference is going to be the same. Now what you'll notice in this particular case is that these will cancel out. Plus 2, yeah, okay, there's positive 2 and there's a positive here, so this cancels out, and then you'll see you have 4x is equal to 0. So in this particular case, x actually holds no, well, okay, let me put this way, x is equal to 0. X is equal to 0. Meaning, we can then look back on our expression, on our original question, and then erase all instances of x and just replace it with 0 or nothing at all. So in this particular case, we obviously put nothing. In this particular case, nothing. And this makes sense because the common difference, second difference, is supposed to be the same. Positive 2, positive 2. Get rid of all the x, get rid of all the x, get rid of that, get rid of that. This doesn't matter. And then we have 8 here, and then we have 0 over here. Now let's check if it's actually, if it works. Right? 0 minus minus 1, that's going to be positive 1, that's correct. 3 minus 0, that's going to be 3. 8 minus 3, that's supposed to be 5, that's correct. And then we can do 3 minus 1, that's 2. 5 minus 3, that's 2. So I've solved for x. X is obviously equal to 0. Now, sometimes the paper actually literally snitches on itself, and because they kind of want you to be on the, to be able to, sometimes they would tell you, okay, let's assume that x is equal to 0, in which case if you get a different value and your value wasn't working, then now you're basically given a value to work towards. Before, maybe let's say you got like 20 and that didn't work, maybe you may have been lost, but now they're telling you that x is equal to 0. So now you can go back to the problem and then try to see, okay, I understand that my problem wasn't working, so how can I manipulate this thing so that x is equal to 0, and you can kind of just work with that end in mind. Now 3.1.2, if x is equal to 0, determine the position of the first term. Remember, position is your n is your position, tn is the term number. In other words, n is kind of like your x and then tn is kind of like your y. If x is equal to 0, determine the position of the first term in the quadratic number pattern for which the sum of the first differences will be greater than 250. This is a bit of a mouthful, so we'll read that again. If x is equal to 0, determine the position of the first term in the quadratic number pattern for which the sum of the first differences will be greater than 250. So those are kind of like your keywords over here. We assume x to be equal to 0. We're trying to find an n number. Okay, we're trying to find that position whereby the sum of the first differences will be greater than 250. Now, what does that mean? What you'll notice over here, and I spoke about this earlier on in the video, is that the sequence created after finding the first differences, 1, 3, and 5, you end up creating an arithmetic sequence. Does that make sense? You've basically just created an arithmetic sequence over here. I could replace this with a semicolon, and you'll realize that's a 1, that's a 3, that's a 5. I'm adding 2 every single time. That's an arithmetic sequence in essence. So what I'm then supposed to do is I'm trying to find an Sn, right? And then we're trying to find Sn for which the sum of the first differences. So these are the first differences, right? We're trying to find the sum of the first differences, which would be greater than 250. So Sn has to be greater than 250. That's what we're trying to solve. We're trying to find the first number where Sn is greater than 250. We're trying to solve for n when Sn is greater than 250. So let's try and actually do that. Remember, it says greater than, not greater than or equal to, greater than. Sn has to be great. Okay, let's put it this way. Let's work with equals first. Sn has to be equal to, and then we know that we are dealing with a with an arithmetic. So we know the two equations that we can use. We can use n over 2, 2a plus n minus 1. We may not need both of them, but if it's possible, let's just know that it may be either one of these two. So we're just going I'm just going to write both so that we can kind of bear that in mind as we're solving the problem. And okay, so now do we have our first term? We do have our first term, but do we have our final term? And the final term is what we don't have. We don't have the Tn. So maybe it may not be beneficial to use this particular equation. So we don't have to worry about this one for now. Okay. So I would like to focus on this particular equation. This is going to be equal to n is what I'm trying to find. So that's going to obviously remain a variable. And I need to try and kind of have all the other letters. So 2 times multiplied by a. What is a? A is going to be 1, I think. I think the sequence was 1, 3, 5 onwards. 1, 3, 5. That's the first difference. Yeah. So I'm going to be putting. So the first term is 2 times 1. So let me just do that. 2 times 1 plus n minus 1 multiplied by the difference, which is positive 2. I'm adding 2 every single time in this arithmetic sequence. That's going to be equal to n over 2, and let's just simplify this. This is 2 plus 2n minus 2. These cancel out. I'm just left with n over 2 is equal to, sorry, Sn is equal to n over 2 2n. Now I want to draw your attention to the keyword over here. The keyword specifically says greater than 250. Greater than 250. That's the keyword to bear in mind there. So I don't want it to be equal to 250. I need it to be greater than 250. So in other words, this is Sn, right? We can agree that this is Sn. Sn is equal to this. That means this is equal to Sn, right? So I can just say n over 2 n over 2, 2n has to be greater than 250. Therefore, I can rewrite this and say n over 2 multiplied by 2n over 1 has to be greater than 250. Right? Sn has to be greater than 250. 2n squared over 2 has to be greater than 250. And then n cancel, n squared has to be greater than 250. Now let's try and actually do this first over here. Let's say I had, I like to work with predictions in mind. If I can kind of predict the answer and what I do kind of matches the answer that I get, then I know I probably did the right thing. So what I can actually do is actually just play around with some trial and error, and then we will get an answer, and then we'll see if the answer we get after we do the maths will correspond to that. So I'm just writing this equation over here. The n over 2 is equal n over 2 multiplied by 2 times n inside brackets. This thing that you see over here, n over 2, and then yeah. So that's all I'm doing over here. That's what my calculator here is supposed to do. So n, let's imagine an n value of, remember we're supposed to be greater than or equal, no, greater than 250. So let's say n was equal to 10. Let's try that. 2 times 10. That gives me an answer of 100. So obviously the sum would not work in that particular case. I need it to be 250. Let's try something like 13. Not going to work. 169, but I'm getting closer. Let me try 16. Okay, 256. Let me try 15. And 15 is less than 250. So I know that the correct answer is 16. So I should kind of expect that. Now let's look at this particular thing. So this is supposed to say n squared is greater, has to be greater than 250. So let me find the square root of that. The square root of 250 is 15.813, right? Greater than 15.813, going onwards, right, in that direction. Now the important thing to note over here is that n you can't be like in the 15.8 position. We're dealing with just discrete numbers in this section, so it has to be 1, it has to be 2, it has to be 3, it has to be 4. So if we talk about has to be greater than, over here is when it's exactly, when it gets to 15.813, that's when we are exactly at 250, but we have to be greater than 250, and we can't accept 15.9, we can't accept 15.95, we can't accept 15.9999999. All those are invalid. We need to have a nice whole number, 16. So 16 is what we're going to roll with, and that's correct. It matches my prediction. So I can then say that n is equal to 16, and that would have been my answer. Now we're not going to go and do this problem properly. I'm just going to kind of explain the concept behind it, and that relates to the 2a, the 3a plus b, and the a plus b plus c thing that I wrote down. Now, where do these things even come from? Let me first give you an example. A(n squared plus bn plus c, a(n squared plus bn plus c, and a(n squared plus bn plus c. Now this is obviously a general quadratic formula, and sorry, I keep saying formula, sequence. It's a quadratic sequence, but in this particular case the ends are going to be different, because you can't have a sequence where the numbers are the same, unless that's the whole point of the sequence. But yeah, this is a general formula. Now obviously, because this is the first number in the sequence, then we can replace this with a 1, so that's going to be a plus b plus c. You can see that a plus b plus c. I've just replaced the n with a 1. Let's replace the n with a 2. That'll be 4a plus 2b plus c, and then this will be replaced with a 3 squared. That's 9a plus 3b plus c. Okay, now what if I were to find the first difference? Remember, this is just a quadratic sequence, right? It's a very general quadratic sequence. We don't know what a or b or c are. So now we're going to do, that's going to be c minus c, that's going to be no c. That's going to be 2b minus b, that's going to be, yeah, 2b minus b, that's going to be 1b, so just b, wait, let me just get this right, 2b, yes, b, and then that's going to be 4a minus a, that's just going to be 3a plus b. Okay, and then let's do this next thing. Again, c minus c, that's just going to be 0. 3b minus 2b, that's going to be 3b minus 2b, that's going to be positive b, right? 3b, yeah, b. And then 9a minus 4a, that's going to be plus 5a. Okay, and then we can find the thing over here as well, that's going to be 2a. Now, it would have probably, okay, let me actually do another line of working out. You can pause to make sense of the math yourself. I just want to put two things so that you can actually see that the second difference is the same, because you can't say that the second difference is the same when you only have one, which is my 2a. Now you'll notice in this particular thing over here is that when I'm following the sequence this way, these first couple of stuff, these are the things that we deal with, the a plus b plus c, 3a plus b, and this 2a. These are for the first numbers in the sequence. This kind of gives us the starting numbers of the sequence, which are a plus b plus c, 3a plus b, and then 2a. So see exactly what it refers to. That refers specifically to this thing over here, the first, the first in the first row. Sorry, let me try and explain that better. This number over here, right? We're following this path over here. So you can't use 2a and then use 5a plus b and then use this particular thing. You can't jump from places to places. Okay, make sure you, when you're using the 3a plus b plus c and the 3a plus b and the 2a, you're following it like this. That's important. In the case of this example, we find the first difference and then we find the second difference, and here we have it. Okay, so this is -6, -6, -9, -15, -21. Now, when you're asked to find the equation of this thing, obviously we can't have an equation that says a n squared plus b n plus c. That's not a good general formula. So what you then do is you do this. You take the 2a and then you equate it to whatever the real value that you get is. So 2a is, you're going to say set it equal to whatever you got. So let me show you what that means. Over here, remember we got a -6. for 2a, in the position of 2a. So you're going to set 2a negative 2 equal to negative 6, and then obviously divide by 2. You're going to get an answer of negative 3. Then you're going to set negative 9. So not negative 15, negative 9. If you're going to use negative 15, then you'd have to use another number. You have to use the 2a, 5a plus b, and 4a plus 2b plus c. Right. So now I'm going to use negative. What do I want to say? Use negative 9. Yes, negative 9 must set equal to 3a plus b, as this thing shows, as the thing that I did shows. And then we're going to do the last one, which is 5, and you're going to set it equal to a plus b plus c. Remember, at every tier, at the 2a tier, you're going to find the value for a, and then you're going to use that value for a to find the value for b at the 3a plus b tier, and then you're going to use that value for a, those values for a and b, to find the value for c at the a plus b plus c tier. And then you've got your expression, right? And you can write in the form of an squared plus bn plus c, negative 3n squared, and then there's no middle term because b was equal to 0, so obviously plus bn, 0 times n, doesn't matter what n is, 0 or b will always be 0, and then plus c, whatever that's constant that you get is. And that's about it for the quadratic sequence. Okay, now for this question 4a. The third term of a geometric series is 7, and the sixth term of the geometric series is negative 2,401. Now, one thing I want you to be careful of is sometimes you may be series, but you may see the word series, but don't be so quick to assume that you're going to be using the series equation. If you're to try and force the series equation over here, you'll find that it won't actually work. So when you the most important part is to know whether it's arithmetic, whether it's geometric, whether it's quadratic. That's the most important part. Sometimes it may seem like a series question, but you may need to use sequence in order to solve it, or vice versa. And in this particular context, we don't even use a series equation over here. We just use sequence concept. Right, because this thing says it's a geometric series, but it talks about the third term of the geometric series and the sixth term of the geometric series. In other words, 1, 2, 3, 4, 5, 6. Now, this is a 5-mark question, so it's not completely straightforward. And when you're stuck like this, when you don't know what approach to take, I always advise you to write what you do know. From writing what you do know, you may be able to extrapolate from that particular point the stuff that you don't know. So just put it down. Put down what you do know, and you may even get some marks for it somewhere along the lines. So put down what you do know. I don't know what the first term is, but that's okay. I don't know what the second term is, but that's okay. I do know what the third term is. The third term is 7. I don't know what the fourth term is, the fifth term is, but I do know the sixth term. It's negative 3,401. So you would see that's quite a jump to get from 7 to negative 2,401. So it's going to be not necessarily a big number, but not a small number either, not like 2 or something. So what number is it going to be? And also we can see that we actually got more negative this side. So we have to be careful about how we go about getting to our answer. Okay, so we're also determine the first term and the common ratio. In other words, a and r. The equation that we can use is Tn is equal to ar to the power of n minus 1, and we're asked to determine that. Okay, now what do you know? Okay, you may think that this is all you know, but you don't. There's a tiny bit more that you do know. What's another word for the first term? Because we don't know that, but how else can I represent the first term? If your answer was A, then you're correct. I can put that there. That's A. Now, how would I get from A to the next term? I'd multiply it by R. How would I get from AR to the next term? I'd multiply it by R. How would I get from AR squared to the next term? And to wrap it up, we have AR to the power of 5. Okay, now we have something that we can actually work with. So if this is AR squared and this is AR 5, and this is 7 and this is negative 2,401, how do you arrive to the answer for this particular expression? Well, the most important part that we have to try and do is to to eliminate a variable. And we can actually do that. We know that negative 2401 over 7 is equal to, what do you think? AR to the power of 5 over AR squared. Now we can actually calculate that. Negative 2401 is going to be equal to, if you do the maths correctly, negative 7. And that's going to be equal to, no, sorry, I'm jumping the gun a little bit. Negative 1,000, I think that's negative 343, right? Let me just double check. Negative 343. That's going to be equal to negative 343. And then on the other side, we're going to get the a's will cancel out, and this is r to the power 5 divided by r squared. So obviously r5 minus 2, that's going to be equal to r to the power 3. So that's r to the power 3. Therefore, r is equal to negative 7. And this is our answer for the common ratio. To get from 7 to the next term, so let's try that out. Let's check if the answers that we got are correct. Multiplying negative 7 from 7, I will get an answer of negative 49. So let me try and put that down, and we're going to see if we can get to negative 2401. 49. Multiply that by negative 7, that gets us to 343, and then multiply by negative 7, you get here. And that's great. So we multiplied it. The closer, the more to the right we go. Now, let's say we're going to the left, we're going in the opposite direction. How would you go about doing that? Well, from 7, if I were to get rid of an r, right? Because I'm trying to get from AR squared to AR, I'd have to divide it by r, right? AR squared divided by r will give me AR. That's what I do. So 7 divided by r, that should give you 7 divided by r, that's going to give you negative 49. So you got negative 49 over here, and then negative 49 divided by r, that should give you 7. No, that does not seem right. 7 divided by negative 7, isn't it? Yeah, okay, I was so confused. Negative 1. And then negative 1 divided by negative 7 should give you 1 over 7. 7. Okay, cool. And you've answered the question. We've been able to solve for we found the common ratio, and we determined the first term based off of that. Here you can just jump to the memo to see a more formal way of structuring things, but you can see it's basically the exact same thing that we did do in order to arrive at our answer. So yeah, you can just have a look at that, but the concept remains the same. And that is the geometric sequence, not about the geometric series. The following question reads as follows. Rectangles of width 1 centimeters from the edge of a sheet of paper. Okay, so let's actually highlight that. Width of 1 centimeters are drawn from the edge of a sheet of paper that is 30 centimeters. Sorry. Okay, 1 centimeter. Alright, so here it is. You can see they are 1 centimeters long, and they're drawn from the edge of a sheet of paper that is 30 centimeters long. So we can see everything starts here, and then it ends here, starts here, ends here. Okay, you can see that. The length of the first rectangle is 21 centimeters, and we can see that's written at the bottom over there, 21 centimeters, and that's the length of the entire rectangle, as well as the width of the paper. It's 21 centimeters. And the length of each successive rectangle is 85% of the length of the previous rectangle until there are rectangles drawn along the entire length of AD. Each rectangle is colored gray. Now, what you'll notice about this is that this previous thing is going to be a fraction of this entire length, right? So let's actually do the math of that. 25, what's 85% of 21? 85% of 21 is going to give me 17.85. This is 17.85 in case you don't know how to do that. 85% means over 100 of 21 of typically means multiplied by, and then you get your answer. Now we have 17.85, and it says each successive rectangle is 85% of the previous one. So then I'm going to take 17.85, and then I'm going to find 85% of that. 17.85, 15.1725, 25, and then I am going to find 85% of that. So 85% of answer, and that gives me 12.89662. I'm just gonna write everything. 12.89662. Now we can actually create a sequence for that, right? Calculate the length of the 10th rectangle. The first rectangle is 21 centimeters in length. The next rectangle, the subsequent rectangle, is 17.85 in length. The next one is going to be 15.1725 in length, and should I write the next one? The next one is going to be 12.896625 in length. Now we're asked to calculate the length of the 10th triangle. Okay, when you also find the length of the nth triangle, the first thing is to first try and find the length of the nth triangle, which basically means finding the nth term. In other words, Tn. So let's find Tn first. So in order to find Tn, we need to know our A and we need to know our R. A is obviously the starting one. We start with the first term of 21. So we're going to put that there, 21, and then, excuse me, we're going to multiply that by R. What's the common ratio? So you're going to do 21 divided by 17.85. Remember, right divided by left. Divided by 21, you get 0.85, which is the 85, where the 85% comes from. And we can just write that as 17 over 20. 17 over 20 over, n minus 1. Right, now we have our general equation, and then we can just write nth term, 21 10th term, so 21 multiplied by 17 over 20, and n minus 1, n is 10 in this particular case, right? We're trying to find 10 for the 10th triangle, and then we get an answer of 4.86395. Now I want to just point something out. You'll notice that R in this particular case is actually greater than -1, but less than 1. Now you may be tempted to think maybe, oh, geometric. It is not a geometric series. The reason why it's not, sum to infinity. The reason why it's not sum to infinity is because there is no mention of infinity. So even if it just has the correct ratio, or the common ratio falling within that sphere, you can't assume immediately sum to infinity. Sum to infinity specifically has to do with when they tell you that we're trying to find what number it tends. So we'll talk about that when you're talking about the sum to infinity. But if we're ending at a specific location, at the 10th triangle, at the 12th triangle, at the 20th triangle, then no sum to infinity. Now when they say something along the lines of what is the maximum number of this, what are we approaching, what is this, or whatever, so when you see something along those lines, then you can assume, okay, sum to infinity. All right, now to answer this problem, calculate the percentage of the paper that is colored. When you're trying to find the percentage of the paper that is colored, what you'd have to do is to find the total percentage, right, of the paper that could be colored, and then how much of that is colored. Total colorable, this is not correct English, total colorable, and then colored. Okay, how much of it is colored and how much of it could have been colored. Okay, what's total colorable? Well, total colorable, if we're talking percentage of something and we're given stuff in length, we can use area. 21 times 30. 21 times 10 would be 210. 210 times 3 would be 630. So 630 centimeter squared is the total colorable. So I'm going to replace that there. 630. Did I say 30? 630 centimeters squared is total colorable. Now, not the most important part here, but how many rectangles can you actually have? You can see we have one rectangle over here, and then we have a space of 1 centimeters. So we can see that there are 30 centimeters that are possible. And then so let's do that. So that's 1 centimeter. Each thing is 1 centimeter, and then there's a 1 centimeter space. We've already used up 2 centimeters just for one rectangle. Then we use up another 2 centimeters just for another rectangle. You'll realize that at this particular rate, then we'd have to use 15 centimeters. We'd have to use 15 rectangles would get us to 30 centimeters. So we know then our nth term is going to be 15. So n is equal to 15. R. A is still equal to 21, and then R is still equal to what we have there. And then now we can use our equation. So let's pull up the formula sheet, and you can see we can use the equation that states this one. Sum to n is equal to A Rn minus 1 over R minus 1. What it'll basically do is just find us how much has been colored, because it'll find this one plus this one. Sorry, it'll find this one plus this one plus this one plus all the subsequent ones up until the 15th one, because you know that's how many rectangles we end up having, 15 rectangles. So yeah, we use 15, you plug that into your equation, and then you find that, and then you do this expression. So you do this over this, and you can just do that on your own, finish that up, but I'll just pull up the memo just so that you can have a look and we can see where it comes from. So you can see there's the 15 that I spoke about, and then we've plugged it into our equation. We get an answer of 127 over 77. So total colorable and then total colored over there, and you multiply that by 100% because we want to try to find this thing in terms of a percentage, and then you get an answer of 20.28%, and that's your final answer, and that is that. Now here we're not told that we're dealing with a geometric series, a sum to infinity type question, but the clue is in this word: if this replication continues indefinitely. So determine the total volume of all the pyramids replicated if the replication continues indefinitely, meaning that it's almost it's like if okay, usually if you're adding something, right, plus 1 plus 5 plus 6 plus 7 plus 7 plus 9 plus 10 plus 11, the number is going to keep on getting bigger. Let's say I reach a number in the billions, then I could always add 1 to that number. It could always become bigger, and it's going to be a completely different number. Now when you're dealing with a sum to infinity, it's a special case of a geometric series whereby we're getting closer to a particular number. If we had done that for the previous problem that we worked on, you'd have noticed that we were actually going to be getting closer to a previous number, and that's because R is greater than -1 and less than 1. Obviously R cannot be equal to 0. It creates a scenario whereby, let me give you an example. Let's say I start off with the number 6. Let's keep it simple. Let's say I start off with the number 16, and then I go to 8, and then let me plus 8 plus 4. You obviously know I'm dividing by 2, so I'm going, no, that's not what I want. Oh no, this is exactly what I want. Yes. Plus 4 plus 2. Right. You do right divided by left, and then you get a half, which has an R value that falls in this range. Now what you'll notice is, let's take a calculator out, and you'll notice that this number over here, the more to the right you go, the smaller it'll get. It'll become closer and closer to 0, almost to the point where it's like we're adding nothing, but we're still going to be adding something, but it's just getting ridiculously smaller. So it's not like the number is getting bigger and bigger, it's just getting ridiculously smaller. So although it'll never be 0, the closer we get to infinity, or if we continue this series on indefinitely, the closer we get to just adding 0. And then that number that it seems that we're approaching is the answer to the sum to infinity. So let's take out our calculator. 16 plus 8, that's 24. Plus 4, that's going to be 28. Plus 2, that's going to be 30. Plus 1, that's going to be 31. And that's pretty much as big as things get, because next thing we do is going to add plus 0.5. That's going to be 31.5. Then plus 0.25. That's going to be 31.75. Then plus 0. I think it's 125. 125. That's going to be 31.875. So it seems though to me right now, just on observation, it seems that we're getting closer to number 32, but I don't think we'll ever reach that number 32. Let's just try and plug that into our calculator. Our first term for the sum to infinity is a, so we're going to I think it was 16. So we're going to plug 16 into our calculator. So plug 16 into your calculator, and then you're going to divide that 16 by 1 minus r, I do believe. 1 minus r, which is a half. And then it should yield an answer of 32. Yes, 32. You see, we're getting closer to that number. We'll never reach that 32, because remember, what we're adding is getting infinitely closer to 0, but we never actually reach 0, and as well, we'll never actually reach 32, but we are going to get closer to that. In this particular case, we're talking about the total volume of the pyramid replicated. So let's talk about the volume of each pyramid. So what you'll do is you'll find the volume of pyramid 1, right? And then we're given an equation, a third of the area of the base multiplied by the perpendicular height. That's 27 over here, and we are told that the base has a length of 9. Okay, the base is 1/3. The base area Okay, so you'll find this thing 81, and then you'll know that, so this obviously the area here is 80 centimeters squared, and then the base area and the perpendicular height was 1/3. So that means that's 81 divided 1/3. 1/3 means I need to divide by 3, right? So 81 divided by 3, and then that's how you get the area for the next one, which I think is 27 yeah, 27 centimeters squared, and then you get an answer over here 27. Also do this one divided by 3. 27 divided by 3 is going to give an answer of 9. That's going to be a perpendicular height, and then you divide again by 3, you divide again by 3, and then you create, and then you've created now a sequence. Now you know that this sequence is going to go on indefinitely, but we are going to be getting closer to a particular number. So what you'll then have to find is, you find your a. What is your a? Well, we found the area of the base, which is 81, multiplied by the perpendicular height, which is 27. That's 2187. 2187. That's our first term. So that's what we're going to plug in for our first term. And then we can then do this one. Remember, right divided by left. So 27 times 9 is going to give me 243 centimeter cubed, because this is area, volume, and then divided by 2187, that's going to give us an answer of 1/9. So 1/9 is our r. So we're going to put 2187 at the top, right? So let me just write that. Sum to infinity is equal to a over 1 minus r. This is going to be equal to 2187, because that's the first area, so it's first volume, divided by 1 minus 1/9, and then you can just find what number you're getting closer to. So 2187 divided by 1 minus 1/9, and then we realize we're getting infinitely closer to 2460.375. I do believe. Let's just check if the memo agrees with us. That's E. It does not, in fact, agree with us, and the reason being is I used the incorrect first term value. I forgot to divide by 3. Remember, it's a third area of base multiplied by the height. So I forgot that part of the thing. That was my bad. But the principle remains the same, right? That's why the common ratio didn't change, because then the thirds kind of cancelled out. But okay, you don't have to think too much about that. But point is, don't forget that. Don't make that silly mistake that I just made. But you get the idea. So you take the one on the right divided by the one on the left, you got out, so you find your a value. So a third multiplied by the area of the base, which is 81, multiplied by 27, that gives you 729. And you do the same thing with this one and the subsequent. Well, you don't need to, you don't need that. You already told that, you already know that it's geometric, so you can just find your r and your a, and then find what we're getting closer to. And that's basically how you solve that particular problem. And that's the end of the video. If you found this video helpful, please be sure to like, share, and subscribe. We'll be coming out with a lot more videos like this for every single section. We'll doing maths. We'll also be adding physical science very soon, and then later on this year we'll be adding English and Afrikaans. So yeah, in order to not miss out, please be sure to like, share, and subscribe, and switch on the bell notification. Message us on our WhatsApp number so that you can be added to the relevant WhatsApp groups as we create them. And see you in the next video.